Um, okay, cool. I think we're all set. Just give me one second. Okay, and I just want to confirm that everyone can see my screen. Okay, perfect. So thanks for stopping in for this physics and organic chemistry content review session. Um, it's generally following the Kaplan book chapters. It should be a pretty holistic overview of sort of like main concepts that the MCAT's going to cover. It won't be super in depth on a lot of topics just like for the sake of time, but hopefully it's enough to sort of jumpstart you into, you know, getting like a refresher on some of this content and, you're studying. So I think what I'm going to do is I'm going to cover physics first, and then maybe we can take like a short break, like 5 minutes or so. And then I'll do Orgo afterwards. And then if you have questions at any point, feel free to drop them in the chat. I'll try to check in periodically and do my best to answer them. And with that, I think we can get started. Okay, cool. So we'll cover physics first. First, we'll do a quick review of just vectors and scalars. So a vector is a quantity that'll have both magnitude and direction. So some examples would include displacement, velocity, force, acceleration. And then scalars will have magnitude only, and a good example of that is speed. And you should know how to do vector addition and subtraction. I have diagrams of two methods here, the head to tail method or the parallelogram method. I personally use the head to tail method. So for these two vectors, u and v, you align the head of u to the tail of v and then sort of draw this line to find the sum. And then when you're subtracting vectors, it's essentially the same process. All you need to do is swap the direction of the vector that you're subtracting. And so, yeah, this diagram here does a pretty good job of seeing how you can just swap the direction of v and you get a different vector here. And you can also just do it by components. Honestly, I think I ended up doing this one a little bit more to get a stronger sense of what direction the resulting vector was going. So yeah, you can do it component wise as well. Here, I just wrote out a quick example of a plus b and a minus b. So yeah, that's just vectors and scalars. So going along with more kinematics and dynamics, displacement will be your overall change in position from final to initial. So here's a good example of the difference between distance versus displacement. So this is the overall like change in position. Your velocity will be your change in displacement over time. So your average velocity you can calculate by doing your change in displacement over your change in time. And then it'll also be the derivative of your displacement versus time graph. And then acceleration will be your change in velocity over time. And it's the same thing for calculating average acceleration. You can just do your change in velocity over your change in time. And this will be the derivative of your velocity versus time graph, or your second derivative of your displacement versus time graph. Here are some equations that honestly I would sort of commit to memory for kinematics. And here it's sort of listed out what variable is missing from each of these. And so you sort of know when it's going to be most useful to you. But I thought just like sort of displaying these straightforward was the best way to just to show you what's most important. So yeah, honestly, just commit these to memory. You'll likely need them. And yeah, they all involve like position, velocity, acceleration, time. Yeah, and then projectile motion is also a topic that will show up. So yeah, you'll have like some object being like following sort of this parabolic trajectory. Like some questions they might ask are like, oh, what's the, the max height of it? What's the total distance it travels? What's the total time it travels? Here are just some like shortcut equations, or some notes that I have as well. So your initial velocity, if like an object's being thrown at an angle, the horizontal velocity won't change. So if you ever need to calculate like the total distance that it travels, like x distance, you can just do the horizontal velocity, or like the x component of the initial velocity, multiplied by the time. And vertical distance, or like vertical velocity, is a little bit different because that's subject to gravity. So you'll need to use like the equations that involve acceleration. So yeah, here's some of them listed out as well. Vertical distance, you can use this equation here. Yeah, again, my notes, horizontal velocity typically won't change. Oh, I forgot to fill this in. But yeah, some things they might ask: the total flight time. If they ask for something like the max height, what you can do is just, use half the total flight time and plug it into one of your equations. And yeah, I also talked about horizontal distance. So just an overview of projectile motion. Then we'll start talking about some forces. So a force is some push or pull that will lead to acceleration, and generally force is equal to the mass of the object times acceleration. And some important forces that you should know are gravity. So that'll be your mass in kilograms times 9.8 meters per second squared. You should know the gravitational constant. And also, if at any point they refer to weight during the exam, that's the equivalent of gravitational force. Your normal force is the force that the surface exerts. So you can see here that like the table is exerting this force back up on the block. And that's perpendicular to your surface. For something like this, it would be equal to the gravitational force because the block is stationary, it's not moving. There's also the friction force. That'll be some friction coefficient times the normal force. I forgot to write it here, but there's usually the coefficient of static friction and the coefficient of kinetic friction. I might be saying that wrong. But roughly it's this formula. And then you also have your elastic force, which will be equal to negative kx, where k is some spring constant, and then x is sort of the displacement of the string. So yeah, these are some forces that you should know of and know how to calculate. Okay, and then we have torque as well. So this is sort of your rotational force. And the formula for this is RF sine theta, where R is your distance from the pivot point to where the force is being applied. So here in green, what they call the perpendicular distance would be equivalent to R. And then F is the force itself. And then this theta is if like the force is being applied at an angle. For these instances here, they're being applied at like a 90-degree angle. So you don't really need the sine theta. So yeah, that's your formula for torque. And then because torque is a vector, you might be asked like what direction the torque is in, and this is where the right-hand rule comes really handy. I did my best to find a good diagram for this. I feel like it might be most useful to, or I'll try and like use my own hand to show you here, but it's also useful to like find YouTube videos and see people like using their hands to do it because it's kind of hard to show. But like for this example here, what I would do is like start with my hand in the direction of like the radius. So it's like going up, and then I would bend my fingers in the direction of the force. So it's going this way. And then my thumb is like pointing towards me. And so like if I'm curving my hand, my thumb's pointing towards me. And so that's the direction of the torque. I did my best to describe it here, but if this is something that's still quite confusing, it took me a really long time to understand. Definitely look up some more examples on YouTube. They'll probably do a better job of like showing it over the screen than I can. But yeah, this is to determine the direction of the torque. And this is all because it's a vector and it's calculated by like a cross product. Okay, I'm just checking, no questions. Okay, cool. And then here's just Newton's laws listed out. It's good to have in mind. So the first law is an object will keep moving as it is unless another force acts on it. The second law is just force equals mass times acceleration. And the third law is every action has an equal and opposite reaction. And I have this little visual here that sort of demonstrates those. And then here I have, oh, now we'll go over free body diagrams. So something that you might see, or I feel like I ran into this a lot on practice problems. I don't know if this was just me, but was these like things on slopes or like objects on slopes. And I feel like it's good to know like quick calculations for these. So okay, let's see where I started first. Okay, yes. So if you're given like this angle here of what the slope is, it's useful to know that that angle will be the same here. So your gravitational force is always going to be like completely like vertically down, but then it can be split up into these different components along like sort of the axes of the slope itself or the ramp. And so this downwards one would be mg cosine theta, and this one along the slope is mg sine theta. Yeah, so gravity can sort of be split up into these two components, where the theta is again this same theta here. And then for this block, because it's stationary, we know that this, or we mentioned earlier that normal force is the force that the surface will exert, and it's perpendicular to the surface. And that's why we see the normal force coming out at a 90-degree angle from the slope itself. And it's aligned with this component of gravity. And so if this block is stationary, we know that these two will be the same. So like if you were asked for the normal force and you know that this block is stationary, you know you can just find this component of gravity. And then again, if we're thinking that this block is stationary, we can set these two forces equal to each other, where this component of gravity is equal to this friction force, hence I wrote mg sine theta. And again, you can also find the friction force by using the coefficient of static friction times the normal force as well. So yeah, it's honestly just having like some practice with this, or sort of knowing these little shortcuts with free body diagrams can be quite useful. So you don't have to spend a lot of time drawing these out or sort of working through these problems in depth. Okay, now going into work and energy. So first, kinetic energy is going to be your energy that's associated with movement. Your formula for that is 1/2 mass times velocity squared. And then potential energy is your energy that's stored within a system. So gravitational potential energy is equal to mass times g, which is again 9.8, times your height. There's also elastic potential energy. Yeah. You also have your elastic potential energy, which is 1/2 kx squared, where k is again like the spring constant, and x is how much it's been displaced by. Here you can see like the spring has been stretched a tad. And then your chemical potential energy is just energy that's stored in chemical bonds. And I think viewing kinetic and potential energy is sort of useful in this diagram, because you can see like let's say if you're like shooting this ball upwards, it's all initially kinetic energy because let's say like we're starting at the ground, but then once it's reached its peak, it's all potential energy because like in that one moment, it's sort of standing still. So all of its energy is potential. And then at these points here, it's 50-50 and we're back at like kinetic energy, at 100% kinetic energy. And then also differentiating two kinds of forces. Your conservative forces will be those that are independent of the path that your system is taking, whereas your non-conservative forces are dependent on the path. So friction is something that depends on like, you know, how far your object is traveling or like how far it's going down the slope and whatnot. Okay. And then we also have work. Work is the process by which energy is transferred from one system to another. The standard unit for this is joules. The formula for this is your force times distance. Power is going to be the rate at which work is done. The standard unit for this is watts or joules per second, which makes sense because it's the amount of work that's being done per some unit time. So in this case, seconds. And then your work energy theorem states that the net work done on a system is equal to the change in kinetic energy. So yeah, I just wrote it out here again. It's the final kinetic energy minus the initial kinetic energy. Okay, now heading into thermodynamics. So temperature is going to be the average kinetic energy of particles that make up a substance. And thermal equilibrium is when systems have the same average kinetic energy. In other words, they have the same temperature. And your 0th law of thermodynamics states that if A and B are in thermal equilibrium with C, then A, B, and C are all in thermal equilibrium. And then I have some not common, but like conversions that you should know, converting from Fahrenheit to Celsius to Kelvin. These are things I would also commit to memory. Obviously for these two, like you only really need to memorize one because you can just plug in the one that you need. But yeah, definitely know how to convert between Fahrenheit, Celsius, and Kelvin. And then thermal expansion. This is when a substance changes in length or volume because of temperature changes, and these are their respective formulas. So like change in length equals alpha times the initial length times the change in temperature, and this is the same thing for volume. And alpha and beta here are special coefficients that would probably be given to you. And then the first law of thermodynamics is just that energy cannot be created or destroyed. And we have this formula that the internal energy or the change in internal energy in a system is equal to plus or minus energy added / lost by the system plus or minus work done on or by the system. I have these plus or minuses because it depends on like if energy is being added to the system or if it's being lost by the system, or if the work is being done by the system or on the system. And what I have in parentheses is like what respective sign you would use. I started phrasing it or like putting it this way for myself because I found a lot of like, or I found different variations of this formula and they all had like worded what Q and W meant differently depending on like what signs they used. And this way was just most intuitive for me. So hopefully it's not super confusing. And then moving on, heat is going to be the energy transfer between two objects at different temperatures. This formula hopefully is a little bit easy to remember. It's Q equals MCAT. And you'll probably use this formula in relation to these phase change diagrams. So M is going to be the mass of the substance. C is going to be your specific heat, which is the energy needed to raise 1 gram of a substance by 1 degree Celsius. And then delta T is your change in temperature. And so you can see here on this phase change diagram that they use this formula at these like sloped parts of the graph to figure out, you know, what heat was involved here. It also states like what states it in. And then in these horizontal positions, that's like the actual phase change itself. And at these points, when you're calculating heat, you're going to use this formula, ML. I don't know why I put heat of transform, where L would be your heat of transformation. And here you can see that they use that one too, like M delta H here. And those will have their own values as well. So just know the different, or when to use each of these. So like at these angled points, or at these like sloped lines, that's when you'll be wanting to use Q equals MCAT. And then at these horizontal points, when they're actually changing phase, that's when you'll want to use Q equals M delta H or Q equals ML. Let me see if there are any questions. Okay, cool. So far, so good. All right, and then continuing on. So there are 4 types of processes that you should be aware of. So isobaric will be constant pressure. Isothermal means there'll be a constant temperature. And this means that your change in internal energy of the system will be 0. Adiabatic means that there's no heat exchange, so delta Q will equal 0. And then an isovolumetric or an isochoric process means that there's constant volume. And because the work done by a gas is equal to negative P times the change in volume, if the change in volume is 0, the work done will also be 0. And you can also find the work done by these systems by finding the area under each of these curves. So you might see this sort of pressure volume graph. And if you like calculate the area under each of these curves, you can see how much work is being done by each of these processes. This is obviously like a really generic one, but you can sort of see like the isochoric one, there's no area under the curve. And so it makes sense that like work is 0 here anyways. And then there are 3 types of systems. An isolated system will just have like no exchange of anything whatsoever. A closed system will only allow for exchange of energy, and an open system is what it sounds like. It'll allow for both exchange of matter and energy. And then you also have state functions. These are functions that are independent of the path that your system is taking. So some examples include pressure, density, temperature, volume, enthalpy, etc. And then you have your process functions that are pathway dependent. And some examples of those include work and heat. All right, our second law of thermodynamics states that the state of entropy of the entire universe will increase over time, where entropy is a measure of how much energy has been spread out. Very simple schematic here. And that the net change in entropy of the universe will never be negative. So we're just like, the chaos of everything is just increasing. Hopefully that's simple enough to remember. All right, now we can move on to fluids. So density is going to be mass per unit volume of substance. So yeah, so it's like your mass over volume. It's indicated by rho, but I just used a lowercase p. Pressure is going to be exerted by a fluid on the walls of its container, as well as on objects placed in the fluid. And the formula for this pressure is force over area. And you can sort of see like the pressure that this fluid is exerting on this cube that's been placed in the tank. But what's not shown here is that the fluid is also exerting pressure on the walls of this tank as well. So there would be arrows like going out, hitting the surfaces of the container as well. Absolute pressure will be the sum of all pressures at a certain point in a fluid. The formula for that is written here, where again, this P is like, this is the density. G times like the height that you're at. And just a quick shortcut is that when you're in water, about adding 10 meters of depth is approximately equal to adding 1 atmosphere to your total pressure. And then you have gauge pressure. This is going to be equal to absolute pressure minus atmospheric pressure. And this is caused by the weight of the liquid above the point of measurement. So yeah, just different formulas for pressure, density, for pressure and density. Sorry, 1 second. All right, now some fluid dynamics. Viscosity is just a fluid's internal friction. So a liquid that's very viscous, like an example of it would be honey. It's like sort of very thick and sticky, doesn't move easily. Laminar flow will be smooth flow, whereas turbulent flow is turbulent as it sounds. Your flow rate will be equal to volume, will be equal to volume over time. This is also equal to the cross-sectional area times the velocity. So for example, if you're like finding the flow rate at this point in this tube, you can do like this cross-sectional area A1 here times the velocity. This equation here is for laminar flow. I think it's Poiseuille's law. Not gonna lie, I had this committed to memory, but I'm very sure that they gave me this formula on the exam. So I guess it's just useful to know like what you would use it for. But yeah, I think the time it came up for me, I just ended up plugging in the numbers that I had given. So yeah, just something to be aware of. The continuity equation relates the cross-sectional area to velocity. So here, I think a good example is like A1, V1 here. So the cross-sectional area is greater here. And if it's equal to like A2, V2 here, that means that the velocity here would be slower, and it would be faster here. So as you would expect, fluids are going to flow faster through narrow passages. And then we have Bernoulli's equation, and this is just a way of relating sort of all aspects of like pressure. So you have like this like big P pressure plus pressure due to like movement. So 1/2 rho V1 squared plus sort of like potential pressure. I don't know. I always recognize that like these look very similar to the formulas of kinetic energy and potential energy. So that's just how I think about it. And it's a way to remember like that these stay sort of constant moving forward. So if you need a way to like relate velocity, density, height, or like figure it out as it's changing like through some tube, or if it's like moving up a tube and like cross-sectional areas changing and all that sort of stuff, you could definitely like relate these equations or like combine them to calculate what you need. Yep, and then the Venturi effect is that the velocity of a fluid through a narrow passage will increase and static pressure will decrease. So this is actually a Venturi tube. And what we said about the velocity of the fluid is, you know, what I said earlier as well. Okay, hydrostatics. So Pascal's principle is when there's an increase in pressure in a fluid, there is an equal increase at every other point in the container. The formula that sort of relates this is just F1 over A1 equals F2 over A2. And then you have Archimedes' principle that when an object is placed in a fluid, the fluid generates a buoyant force against the object that is equal to the weight of the fluid displaced. Excuse me 1 second. Sorry. So the formula for buoyant force is going to be rho. So the density of the liquid times the volume times the gravitational constant, 9.8. And then you can figure out if your object's going to float or sink depending on if the buoyant force is greater than the force of gravity of the object. So you can see here if it's greater than, if your buoyant force is greater, then the object is going to float. If the buoyant force is less, then your object is going to sink. And that's sort of, you can sort of see that here. Also just by like comparing densities in general. But if like you weren't given density, you would be able to determine that by looking at buoyant force as well as the gravitational force of these objects. And then specific gravity, that can be calculated by dividing the density of the object over the density of water. And then we can talk about cohesive and adhesive forces. Sorry, I'm sort of following along these bullets as I put them. So your cohesive forces are going to be between the same fluid, as I have here, like the water molecules are both interacting with each other. And then your adhesive forces are going to be between different materials. So the way the water is interacting with, let's say this is like some bent container. So those are going to be your adhesive forces. So a good example of cohesive forces are like the way water molecules interact when you're like stacking them on a penny. I don't know if anyone else did this lab in like high school. But yeah, all the water molecules like sort of bubbling over on this penny, those would be cohesive forces, and then an adhesive force would be like maybe between water and the penny itself. Yep, and then, oh yeah, this is just a visual of Pascal's principle, what we said about F1 over A1 equals F2 over A2. So this is the principle that's used for hydraulic lifts. As you can see, the force that you put down here on like the smaller area will produce a related force on this other end with a larger area. And you can calculate what that force is by using the formula of Pascal's principle. All right, we move into electrostatics and magnetism. So a little bit different. Some of this, I mean, some of it might overlap from chemistry. I was just saw protons and electrons. So both protons and electrons will have a 1.6 times 10 to the negative 19th Coulomb charge. That's a constant that I had sort of committed to memory. It might be useful to have that committed as well. Okay, just general to know, opposites will attract. So if two things are positively charged, they're going to repel each other. If they have opposite charges, they're going to attract. Your Coulomb constant, this is something also to commit to memory, is 9 times 10 to the 9th newtons meter squared over Coulomb squared. And this here is Coulomb's law, calculating the force between two charges. So the force equals K Q1 Q2 over R squared, where R is like this distance between them. And then every charge will also generate an electric field, and you can calculate that electric field by this formula, E equals KQ over R squared. And then electric field lines, which you can see in this diagram here, they'll always go away from the positive charge and towards the negative charge. As you can see here, like the arrows are going out of the little plus sign and towards the little minus sign. Okay. And then two other concepts related. Your electrical potential energy, symbolized by U, is the amount of work required to bring a test charge from infinitely far away to a given position. The formula for that is written here, U equals KQ1 Q2 over R. So similar to the force formula that we saw earlier, except the R is not squared. And then your electrical potential is your electrical potential energy per unit charge. Voltage is also related to this. So it's your change in potential as you move a test charge. So if you're finding voltage, you're finding like the change in electrical potential over two positions. And the formula for that is just KQ over R. And again, those are written out here. And your Coulomb constant is the same as what we said earlier before as well. Here. All right. Electrostatics and magnetism. So wires that are carrying current, they'll generate a magnetic field. And the formula for that is mu naught I over 2 pi r, where mu naught is this constant here. Something else also to commit to memory, 4 pi times 10 to the negative 7th. I is your current, and then r is like the distance from which you're at, like the distance from the wire that like you're measuring the magnetic field. So the distance or the strength of the magnetic field will change depending on the distance that you're at. So like let's say I'm arbitrarily measuring from this green point here, that would be what my R is. And then this is also something that you'll probably want to use your right hand rule for in determining what direction the magnetic field is going in. So and just like put my hand in the direction of like the wire and your thumb in the direction of the current, and whichever way like your fingers curl, that's the direction of the field line. So this one will be like circular as opposed to one direction. And then yeah, this formula is one to commit to memory for sure. And then the magnetic field of a loop of wire, this one is pretty similar, except there's no pi involved. These are all like quite simplified from a larger equation that I can't recall for some reason. But honestly, if you just memorize these, hopefully that's enough, because there's no point in doing the entire derivation when you sort of have these committed to memory anyways. And again, this is just showing you how you can do the right hand rule for a current that's going in a loop. All right, and then these magnetic fields, or like these, yeah, the magnetic fields can generate these forces on other current carrying wires or point charges as well. So the force of like one magnetic field from a current carrying wire on another can be measured by this formula here, ILB sine theta, where B is your magnetic field from earlier. So where R in this case would be like, let's say you're measuring the strength of like this, of the force from like where this wire is, like the distance between them would be your R. L is like the length, and oh yeah, sine theta again, that's if they're like angled, but honestly I feel like that's quite complex for what's expected. But yeah, that's just, again, so you know it's like a cross product. So yeah, that can be between two wires. And then if you're finding the magnetic force on a charge from a current carrying wire, you can use this formula of QBB sine theta. So here you have like your current carrying wire. This charge, it involves some velocity. And then Q is the charge of the molecule, or of the particle itself. All right, we'll head into circuits. So just two things to note. Conductors are materials that will allow for the passage of electrons or current. Metallic conduction will involve flow of current due to electron movement, and electrolytic conduction will involve the movement of free ions under an electric field. And insulators will resist the movement of charge. So with circuits, they will also involve capacitors and resistors. Capacitors will have the ability to store electric potential energy, and the formula for capacitance is Q over V, where Q is a charge, V is the voltage. These are some formulas that you should also know. They will probably come up in like any sort of circuit problem. Knowing the electric field inside a capacitor, determining capacitance, not from this formula, but instead like the geometry of the capacitor itself, as well as like potential energy of the capacitor. Dielectrics are insulators that can be placed in between a capacitor, and that'll increase its capacitance by some constant K. So yeah, dielectrics will increase capacitance. And then resistors are materials that will slow down electrons without stopping them. And this is your formula for resistance if for some reason you're asked to calculate that as well. All right, and then I just have a lot of pictures of circuits here. This is a chart that I would definitely commit to memory as well. I keep saying that, but it's easy to commit a lot of things to memory. So it's like, it's quite fast to go through these problems. So for your resistors and capacitors, know how you can find, like, relate, or for resistors, R equals V over I, or V equals IR, where again, I is your current, V is your voltage, R is your resistance. Like your capacitance equals your charge over your voltage. And then these are like resistors in parallel. So if you ever need to like simplify a circuit, or like you would want to simplify this circuit into just being like one, because you have these three resistors in parallel, and you can combine them using this formula to find like this resulting resistance. So you just write it as one. And then these are resistors in series, and you can also just like sort of redraw that as one circuit with one resistor by simplifying it using this formula here. And then this is like sort of the same thing that you can do with capacitors, and their formula is like swapped with the series and parallel of resistors. And yeah, like this is just combining the two. So you would be able to like combine these two resistors because they're in series. Yes, they're in series. And then you would be able to do a bunch of calculations with like current and charge and whatnot moving forward. I'm going to try and speed through a little bit. So some other things to be aware of for circuits are Kirchhoff's laws. So the junction rule is that the current going into a junction will be equal to the current leaving the junction. An example here is this current coming in and the two currents coming out. So like the sum, like IC will equal I1 plus I2. And then your loop rule says that in a closed loop, the sum of voltage sources will equal the sum of voltage drops. So like the change in voltage, or the increase in voltage in here, is going to be equal to the change in voltage drop in this loop, as well as this overall loop as well. And then Ohm's law is V equals IR. And you'll probably recall that was right here, just rewritten in a way to recognize resistance. Right now we'll move into waves and sound. Here's just a quick review. So your wavelength is the distance between like two peaks or two troughs. Your amplitude is sort of from like the halfway point up. Your frequency is going to be the number of cycles your wave makes per second. So this is something that would be low frequency. This is high frequency since it's making a lot more movement per second. And then the period is the number of seconds it takes to complete a cycle. This is also the inverse of your frequency. Also important to know that your troughs are also called antinodes. And like these intersection points are going to be called nodes, or like they would also be like points here. For interference, you can have both constructive and destructive. So if you add waves X and Y here, you'll get a resultant wave that's greater because these two, like, if you can tell, like their peaks line up, their troughs line up. So it adds up to make a larger resultant wave. Whereas in this case, they actually cancel each other out because they're misaligned. So like the peak lines up with one of the dips in the curve in the wave, and that just keeps happening. So you get no resulting wave. This is supposed to be. Oh, and then this is the difference between a traveling wave and a standing wave. Yeah, I thought this would be the best way to see it. So you can see that like this one, it's like actively moving across the screen, whereas this one, it sort of involves shifts in amplitude in the same phase. So just two different types of waves, traveling waves and standing waves. All right, so moving on sort of to sound. Sound will propagate fastest through solids, then liquids, then gases. Or as like density increases, your speed of sound will decrease. Pitch is our perception of frequency. Intensity is related to a wave's amplitude. It's also equal to power over area. I don't know why I don't have more on that. I feel like if they'll probably give you power, or I might be missing a formula here. I apologize for that. Um, and then what I think is most important about sound is the Doppler effect. So this is the perceived shift in frequency when a sound source or a sound detector is moving. So it's like as an ambulance is sort of driving away from you, like it gets like it sounds different as it's moving away or as it's approaching you. And the formula to determine that sort of like relative frequency is this formula here. Again, something to commit to memory. The numerator is related to the observer and the denominator is related to the source. And you can sort of intuitively assign like the plus and minus based on like if you expect like frequency to increase as something's approaching, a person or decrease. But this is also written out for you on here. And then quickly about harmonics. So the first, second, and third harmonics for a tube that's open at both ends, or a pipe that's open at both ends, as well as one that's closed at one end, are displayed for you here. And the associated formulas that you should know for both of these as well, where like the length equals n times wavelength over 2, where n is some constant, 1, 2, whatever. But for this formula here, notice that it's only odd multiples. So here they have like 1, 3, 5, 7, whatnot. Yeah. Oh, and as a shortcut for strings that are attached at both ends, the number of antinodes that are present will tell you which harmonic it is. All right, light and optics. So this is just the electromagnetic spectrum. As you have, you'll have increasing wavelength as you approach like red or like radio waves and all this, but less energy, and you'll have, as you like decrease wavelength, you'll have increasing energy. So like gamma rays, X-rays, like your purples, those will have more energy. I think just associating or knowing the relationship between energy and wavelength is most useful. All right, and then the double split, or I should go over it. Diffraction is the bending or spreading out of lights as they pass through a slit, as sort of seen here. And then Young's double split experiment, I highly recommend being, what do you call it, familiar with. Sorry. This is, I thought I'd linked it. If you guys might be familiar with the organic chemistry tutor, they had a really good video about it, and I recommend watching that. But it goes over these formulas and how you can sort of identify these different like beams that you can see in the split experiment, and the numbers that you need to use or like what those are associated with. But yeah, I would definitely go take a look at that. Laws of reflection and refraction. So reflection is quite literally what it sounds like, that these angles are going to be identical. And then refraction, you should know Snell's law, as well as where n is like this constant that's related, or it's the refractive index, and it's related to the speed of light in vacuum or air over the speed of light in a medium. You might be asked to calculate this. And then like relating it to like light traveling through two different mediums, you can use Snell's law right here. And then for mirrors, you should know the mirror equation, which I have here, where F is the focal, or the distance from V to F. V. The focal length, and then DO is the distance from the object to the mirror, and DI is from image to the mirror. This is also something that I would sort of memorize. It makes things a lot easier. And I think it's useful to know how to draw ray diagrams to be safe in case you run into any of these. Bozeman Science had a good collection on how to draw ray diagrams for all different kinds of mirrors, whether they're like concave or convex. The same goes for lenses. He had them like good videos on how to draw ray diagrams, and I like watched them all. So I'd highly recommend checking those out as well. But yeah, mirror equation, knowing what sort of images concave and convex mirrors produce as well, and ray diagrams. Yep, and then your types of lenses, again, something to commit to memory. The thin lens equation, something also to use, it sort of lets you know where the image produced by something going through, or some object being put through a lens, where it will be produced. Knowing what like a converging lens is and a diverging lens is, and how light sort of travels through them. Oh, and also just a formula to know that the focal length is related to the radius of curvature by dividing it by 2. All right, atomic and nuclear phenomena. Sorry, I'm trying to speed through, so we have time for orgo as well. Planck's constant, a constant that you should know you should definitely know. The photoelectric effect is just an ejection of an electron from the surface of a metal in response to light. This relates to energy of a photon, or energy of a photon of light will be equal to Planck's constant times the frequency of the incident light. You can calculate wavelength from frequency by knowing that the speed of light 3 times 10 to the 8th is equal to frequency times wavelength. And then threshold frequency is just the light frequency necessary to eject an electron from a given metal. And your work function is the minimum energy necessary to eject an electron from a given metal. All right, and then emission versus absorption. So absorption involves like an electron moving like up orbitals, whereas emission it's moving down. And you can sort of see here like the difference of what it's absorbing versus emitting. The Bohr model states that electron energy levels are stable and discrete. Sort of, you can see here that they're like discrete energy levels. And fluorescence is when a species absorbs high frequency light and returns to its ground state in multiple steps. All right, nuclear reaction. So fusion versus fission. So fusion is what it sounds like. They're small nuclei combining into larger nuclei, whereas fission is a nucleus splitting into smaller nuclei. Both energy will be released in both of these processes. And then for radioactive decay, definitely be familiar with all these types. So alpha decay, beta negative decay, gamma decay, as well as electron capture. There's quick shortcuts in knowing like how the mass or atomic numbers will change associated with these types of decay. So it's like a neutron turning into a proton turning into a neutron. Sometimes there's no change. I think for gamma ray, there's no change. So if you're like displayed with something of like this sort where it's like, oh, it's changed from this to, you know, AXZ -1, like what kind of emission was involved, or like what type of decay was involved. So definitely be familiar with these as well. Right, exponential decay. I'll sort of leave this on the screen. Hopefully, it's more so just like being familiar with this formula and knowing how to use it. Hopefully you guys have seen some variation of this as well. All right, and then just some shortcuts for math. Definitely know prefixes, symbols, and like what multiple of 10 it is. Rounding will help you save time. Scientific notation is also your friend. It helped me a lot. Like instead of trying to navigate a bunch of different, you know, prefixes and whatnot, just convert everything to scientific notation. And remember your logs as well and how to work with them. These are like, I think, basically should cover what you should know, or like how to manipulate logs as well. Reasoning about design and execution of research. I think the most important thing to take away from here is the difference between accuracy and precision, because I would confuse those two a lot. But I think this diagram is quite useful. So accuracy will be how close your experiment is to measuring the true value, whereas precision is how consistent your results are. It'll probably be like asked like, oh, this is precise but not accurate. or like, they'll give you some paragraph and you'll have to determine um, what like the nature of the experiment was. All right, and then there's just different types of bias relating to research experiments they should be aware of: selection bias, detection bias, the Hawthorne effect, as well as social desirability bias. Hopefully you can read through those on here. And then different types of variables, besides just your independent and dependent variables, you have your mediator and moderator variables as well. And this diagram helps clear that up. So mediator is like how sort of the independent variable affects the dependent, and your moderator variable, which influences the existing relationship. Right, and then here's just some basic stats that I think you should be familiar with as well. So you have your mean, median, mode, your range. This is what a normal distribution looks like. It's when the mean, median, mode are equal, as you can see in the middle here. Know the difference between independent events and mutually exclusive events, as well as know that like a type 1 error is when you have a false positive and a type 2 is when you have a false negative. And then here are just some skewed distributions as well, and like where the mean, median, and mode are in relation to those skewed distributions. Okay, it's 7. I know I took a little bit longer than I would have liked to going over physics, but we can take like a 5-minute break so people can use the bathroom and drink some water. And we can go over physics right after that. So we can take a few minutes. All right. We can get back into it. So I'm assuming everyone can still see my screen. I don't think I changed anything. So we'll go into Orgo now. I might go a little bit over time, and I'm sorry about that, but this will be uploaded to um, your team's channel, as well as hope I can share this presentation with you guys as well. Okay, for Orgo, first some general nomenclature. Alkanes will be hydrocarbons that only involve single bonds. The general formula is for the amount of carbons that you have, the number of hydrogens will be twice that amount plus 2. Those will all end in ane. Alkenes have a double bond and those end in ene. So it like matches the ending that you can see here. And the same goes with alkynes, which have triple bonds. Alcohols have an OH group. The prefix would be hydroxy, or the suffix would be all. So if you see either of those, then you sort of know that an alcohol is involved in whatever molecule that you have. And then if you see diol, that involves 2 hydroxyl groups, so 2 of these OH groups. A carbonyl involves a carbon double bonded to an oxygen, which you can see in a lot of these here. And then a carboxylic acid has this group here, COOH, and those will end in oic acid. So here we have the different primary, secondary, and tertiary alcohols. Same with amines, which have this nitrogen and then like a variable amount of hydrogens attached. And then different variations of carbonyls, which we'll see more of later as well. And then also these prefixes you should also be familiar with when it comes to like identifying molecules, what like each of these prefixes is and like how many carbons that means is associated with that molecule. So if you see like butane, you should know that that's like 4 carbons, and it's only single bonds. Okay, for isomers, so a chiral center will be when 4 different groups are attached to a central carbon. So an example is right here where you can see attached to this carbon, you have a methyl group, a hydrogen, a chlorine, and this ethyl group here as well. So this is a chiral center. And then there's 2 different kinds of configurations associated. So you have D and L configurations, excuse me. And this is stereochemistry that's in comparison to another compound. And you see it with sugars and carbs a lot. I think I saw it mostly with sugars. So here you can see the difference. It usually has to do with this OH group and whether it's on like the left side or the right side. So hopefully that helps identify like L versus D. And then for absolute configuration, you have your S and R configurations. This involves Kohn-Ingold priority rules. So you would order the atoms at this chiral center by highest atomic number, or by double, triple bondedness, and you would want your lowest priority to be in the back. After you set this priority, if you like draw sort of an arrow, or like when you're going through them, if you find that it's in a clockwise order, you have an R configuration. If it's a counterclockwise order, you would have an S configuration. So here, because it's clockwise, this molecule has an R configuration. And then you have your E to Z stereochem configurations that are used for alkenes, and it has to do with whether like these substituents are on the same or opposite sides. So Z is for same, like Z kind of sounds like S. That's how I remembered it. So like same side, or E is opposite sides. All right. So your stereoisomers will only differ in 3D orientation, but they're bonded the same exact way. So these will involve conformational isomers, which only require rotation. And your 3 types that you should know are anti-gauche and eclipsed. So I have those sort of drawn out here. And then your configurational isomers, those will be your enantiomers, diastereomers, enantiomers and diastereomers. So here you can see enantiomers are non-superimposable mirror images. So here we have an example of enantiomers. They are non-superimposable mirror images, like you can put them on top of each other. And diastereomers will not be. And you can see the relationship between like R and S configurations and whether that means that like two compounds are enantiomers or diastereomers. So if they have like if all the configurations are swapped, you can see that they're enantiomers, so like RR to SS or SR to RS. But if only one of them is swapped or not all of them are swapped, then they're diastereomers. So that's also a way of identifying like what type of isomers two compounds are. A racemic mixture will be a 50-50 ratio, will be 50% of each type of two enantiomers. And then meso compounds, these will have a plane of symmetry and they will be, quote, optically inactive. So if you're like shown a set of compounds, then you need to identify the one that isn't optically active, then you could find the meso compound. So an example of that is here because there's a plane of symmetry going through this molecule. So this is a meso compound. This chart is sort of useful in navigating the different types of isomers. So stereoisomers. Oh, and I didn't go over constitutional isomers, and that's just when molecules have the same molecular formula, but they're bonded like completely differently. It doesn't have to do with just rotations or orientations in space, anything of that sort. But yeah, this is sort of useful in initially navigating what kind of isomers different compounds are. Right, now for bonding, here are the quantum numbers. You should be familiar with all four of these. The principal has azimuthal, the magnetic, and the spin, and the possible values that each of them can have. These will describe the size, shape, orientation, and number of atomic orbitals in an element. And this chart here helps sort of understand the relationship between it says here as well, like in the notes, like what different quantum numbers specify, or like what kind of orbital it specifies, but there's only like a unique set for each specific orbital. These formulas are also helpful. So in terms of knowing the maximum number of electrons, in terms of n, you have 2n squared. The maximum number of electrons in a subshell, it'll be 4L plus 2. So you're using different quantum numbers here. All right, and then you have molecular orbitals. These can be both bonding or anti-bonding orbitals. Bonding orbitals will be the overlap of orbitals of the same sign. These will be more stable than anti-bonding orbitals. So you can sort of see the difference here. And then you have your sigma and pi bonds. I think what's most important to know here is that single bonds are composed of one sigma bond, and then, or that single, double, and triple bonds are all composed of only one sigma bond. But the difference is in the number of pi bonds that each of these have. So double bonds have 1 pi bond, triple bonds have 2 pi bonds. All right, and then you have hybridization. You can have sp2, sp3, sp4, etc. Orbital hybridization. And I think the easy way sort of to identify like how a molecule is hybridized here is like counting how many things it's attached to. So like this carbon here, it's attached to 3 hydrogens, and this other carbon here. So it's attached to a total of 4 things. And then if you add up all the exponents here, there's like an invisible 1 here with the S and then a 3 with the P. So it's like it adds up to 4, and this carbon is bonded to 4 things. And then you can do the same thing with like this carbon here. Like this carbon here is bonded to 2 hydrogens and 1 carbon, so it's sp2. But when you add the exponents, you get 3. that was just sort of how I was able to easily identify it. And I have more examples here as well. And then conjugation and resonance, that just has to do with how, like, the characteristics of these alternating double bonds and how, like, the electrons can sort of shift around. This typically makes a molecule quite stable. It makes a molecule easy to stabilize. So like the electrons from this double bond jump onto this oxygen here, leaving like a temporary positive charge. This double bond can move over and the positive charge moves here. This is like something important to know for reactions moving forward. Now for acids and bases, you'll most likely come upon Lewis acids and bases, as well as Bronsted-Lowry acids and bases. And the difference has to do with Lewis acids and bases are talking about electrons, whereas Bronsted-Lowry acids and bases are talking about protons. And here you can see in this example here how they've sort of identified the two different types. So your Lewis acid will be an electron acceptor, whereas a Bronsted-Lowry acid is a proton donor, and it's vice versa for their bases. And then, excuse me, amphoteric molecules can act as either acids or bases, just a term to know. And then your acid dissociation constant, Ka, which is calculated like here for you. You should know that a larger P or a larger Ka means that you have a stronger acid. That means a smaller pKa means you have a stronger acid, because when you see the term P in front, it just means you're taking the negative log of whatever's in front of it. So the negative log of a large Ka is small. All right, nucleophiles and electrophiles. So nucleophiles are, quote, nucleus loving. So these will contain lone pairs or pi bonds, and they often carry a negative charge. Factors that affect it will be like how much charge it has, as well as steric hindrance. On the other hand, electrophiles are, well, electron loving. So they'll likely contain a positive charge or will be positively polarized. Two types of reactions definitely to know are SN1 reactions, which are 2 steps, and SN2 reactions, which are 1 step, and involve an inversion of stereochemistry. So I know this is a little bit confusing, but just think like SN1, SN2, they mean the opposite of what they actually are. So here I have a diagram of the SN1 mechanism, where there's like this leaving group, or the leaving group going is 1 step, and then the nucleophile coming in is a 2nd step. And then your SN2 reaction is like 1 concerted step, where the nucleophile comes in and this leaving group leaves at the same time. And the rate of both of these is also written. So the rate of the SN1 reaction is written here. This is the rate of your SN2 reaction. This is just an easy chart, something that I sort of committed to memory in terms of like what kind of solvent that we might see. I've written out like what different types of polar protic versus polar aprotic solvents you might see. So what the substrate is and what kind of solvent you're in and what type of reaction you're most likely to see. It was useful for me, feel like it would be useful to most others as well. So I sort of included it here for you to be able to commit to memory. And then here's just a small like diagram of SN1, SN2 versus E1 and E2. These elimination reactions involve like the elimination of something, and you'll see a double bond in place of it. All right, redox reactions. So these will involve the transfer of electrons. This diagram here is talking about sort of how to determine the oxidation number or the oxidation state. It's if you treat like all the bonds as ionic and what it would be. You can like take a closer look at this to determine how they did it for all these different ones. But if a molecule is being oxidized, its oxidation state is being raised and it's donating electrons. Whereas if it's being reduced, it's a reduction in the oxidation state and it's accepting electrons. You'll probably see the terms oxidizing agent and reducing agent as well. So it itself is the opposite is happening to it. So if it's an oxidizing agent, it's doing the oxidizing, but it in return is being reduced. And the same goes for a reducing agent. It itself is doing the reducing, but or it's doing the reducing, but it itself is being oxidized. Right. For alcohols, just again from nomenclature, the molecule will have the suffix "ol" if it's the highest priority, otherwise the prefix hydroxy. Phenols are benzene rings with OH groups. So like if this X was an OH group, that would be a phenol. These can hydrogen bond, or alcohols can hydrogen bond. And phenols are more acidic than other alcohols. The ring can delocalize the charge of the conjugate base. And then these are just different positionings of where the alcohol group can be, and like what these prefixes, if you see them in like the name of a molecule, it'll help you identify like where the alcohol group is. So ortho, para, and meta. So primary alcohols can be oxidized to aldehydes by PCC. I have a table on oxidation and reduction that you'll see in a few slides that sort of summarizes this, but I thought to include it here as well. So they can be oxidized to aldehydes by PCC, and it can be oxidized to carboxylic acids by even stronger oxidizing agents. Secondary alcohols can be oxidized to ketones. Alcohols can also be converted to these mesylates or tosylates to make them better leaving groups for nucleophilic substitution reactions. And on the other hand, aldehydes and ketones can be protected from being reduced to alcohols by converting them into acetals or ketals. So acetal, of course, relating to an aldehyde, you can see like the hydrogen group here, or ketal for like ketone. All right, phenols, which we saw, or we discussed a little bit earlier, these can be oxidized to make quinones. This is an example here where it has like this double bonded oxygen. Ubiquinone is the same as coenzyme Q, which you're probably familiar with from the electron transport electron transport chain. But yeah, just something to know is that like that's a quinone. All right, this is the table that I was talking about. It was common oxidizing and reducing agents. Definitely know this table for sure, and know like the strength of these different agents. And so, okay, this slide's about aldehydes and ketones. So these are commonly produced by the oxidation of primary and secondary alcohols. And they can be reduced to form alcohols as well. So you can see on the reducing agent side of things how it can be reduced to make different kinds of alcohols. And yet be mindful of the strength of these agents, because some can convert a primary alcohol, like this PCC can convert a primary alcohol to an aldehyde, but it won't convert it to a carboxylic acid, whereas KMNO4 can. And yeah, like LiALH4 can reduce a carboxylic acid to make an alcohol, but NABH4 wouldn't be able to do that. So this table is very important for sure. Aldehydes and ketones for nucleophilic addition reactions. This is sort of the general mechanism where this nucleophile comes in at this carbon, where the carbonyl carbon, it'll push the electrons onto this oxygen, and it can be protonated, and you have this alcohol here. So this is when there's no leaving group. However, if there is a leaving group, like let's say one of these R's is a leaving group, then that R would be kicked off and the carbonyl would be reformed. These are some common reactions with aldehydes and ketones that I would definitely be familiar with. And you'll come across some form of this, but you'll see a lot of these involve just like attacking the carbon of the carbonyl, and some sort of like substitution is happening. I won't get into specific mechanisms now, but I've sort of summarized them here. All right. enolates. So here, oh, where am I going? So alpha hydrogens are these hydrogens here that are next to the carbonyl carbon. So this is your alpha carbon, beta carbon, and so your alpha hydrogens are here. These are relatively acidic. So just something to know if you ever see these like show up in a reaction or like with some base. Um, and then here you have enols and enolates. So enolates can be stabilized by resonance with the carbonyl. So you can see like this double bond can move upwards. So that's also something to be aware of. The next point is ketones are generally less reactive towards nucleophiles due to steric hindrance. Aldehydes will generally be more reactive than ketones. And then another thing to know as well is that the keto form of an aldehyde or a ketone is more common than the enol form. And it kind of makes sense because this is how you'll most often see like what a ketone looks like. You probably won't see this double bond shifted down in an OH instead, but just know that like this can happen and you might see it this way. So something to be aware of for sure. This is another important reaction is an aldol condensation. So an aldol is an aldehyde and an alcohol. And this mechanism goes through it quite well. I won't go through the entire thing right now just for time's sake, but you can take a close look for sure. Definitely be aware of this. It's a common way of like combining these two molecules. All right, carboxylic acids. These are always terminal groups. They're polar and they hydrogen bond well, and therefore they have a high boiling point. The acidity of carboxylic acids is enhanced by resonance between oxygen atoms. And this can be enhanced by electron withdrawing substituents. So here I've sort of written like this is going to be your strongly acidic hydrogen and your basic centers. But if you have something like a beta dicarboxylic acid, so something like this alpha hydrogen is going to be the most acidic due to resonance. So if you were asked, like, if you were given this molecule and asked in some reaction, like, or like, what's the most acidic here, it wouldn't be one of these hydrogens, it would be this alpha hydrogen. Some common reactions for carboxylic acids, they're involved in a lot of reactions. So again, for oxidation and reduction, definitely know what, again, like I said before, know like what solvents will be able to actually oxidize and reduce certain molecules to produce what you'd like. So like what will convert an alcohol to a carboxylic acid, or what will be able to reduce a carboxylic acid back to an alcohol. So I have these listed out here. These are some additional ones that the table didn't have, but definitely know those as well. And these are some like diagrams of reactions that I think you definitely should know as well, that carboxylic acids are involved in. So you have this is like a general one with nucleophiles. So your nucleophilic acyl substitution, again, you have your nucleophile like attacking the carbonyl. But yeah, in acid halide synthesis with SOCL2 or PBr3, these are really common ones. And then you have your amide synthesis, anhydride synthesis, and ester synthesis as well. Just be familiar with these for sure, and like what can be made from them. All right, then you have your carboxylic acid derivatives. Also, I'm realizing it's 7:29. I'm gonna keep going till the end of the presentation. I'll probably be a little bit sweeter, but I'll record this whole thing or I'll upload this whole thing and also a link to this presentation so you can take a look yourself. But yeah, just wanted to put that out there. So your carboxylic acid derivatives, they're all sort of listed out here. And then here are some small notes that I thought were important. So cyclic amides are called lactams. A Fischer esterification is an important reaction to know as well. This involves carboxylic acids and alcohols, and that mechanism is drawn out here. Also know that cyclic esters are called lactones. So I have like a lactone here and a lactome here. And this is like the non-cyclic version for amides and esters. And then as well, important to know, anhydrides are condensation dimers of carboxylic acids, and the synthesis of that is sort of drawn out here. For reactivity of these carboxylic acid derivatives, I would know this order for sure. So this is actually written out from like most reactive to least reactive. But yeah, acid chlorides will be most reactive. Amides are the least reactive of these derivatives. And these are some things that can influence reactivity. So steric hindrance, the more electronegative groups in a carbonyl containing compound will result in greater reactivity. Conjugated compounds will also be more reactive, and increased ring strain will also mean that they're more reactive. All right. So we'll jump into amino acids just for a little bit. So this is the general structure. So you have your carboxyl group, your amino group, your side chain, and your like central carbon here. This alpha carbon is chiral in all amino acids except glycine. All amino acids are L amino acids and all have S stereochemistry except for cysteine. Amino acids are amphoteric, so they can act as both acids and bases. And then the peptide bonds formed for making peptides, they're formed by condensation reactions that can be cleaved hydrolytically, and I've roughly like shown it in these two images here. So here's like the formation of the bond, here's the cleaving of the bond. Yeah, and you can take a closer look, but I think roughly what's most important to know is that like water is involved in this bond formation. And then for the synthesis of amino acids, the two ways to synthesize an amino acid are the Gabriel synthesis and the Strecker synthesis. Not gonna lie, I wasn't super familiar with these besides the names of these two reactions. I feel like I should have more sound advice to give on this. But if you'd like to study the mechanism more, like I've sort of listed out the different reactants here and taken these images so you can see exactly how amino acids are made. But I think it's important to just sort of be aware that the names of these two reactions are how amino acids are made. All right, and then just a quick note on phosphoric acids. This is the structure. They act as a buffer over a large range of pH values, and in forming phosphodiester bonds in DNA, a pyrophosphate is released, and that mechanism is sort of displayed here as well, and you can take a closer look if you'd like. So now we're going to be talking about spectroscopy for a little bit. So first, IR spectroscopy, that's like these sort of large graphs that you'll see with these like huge curves. This measures the absorption of infrared light, which causes different types of molecular vibration, like stretching, bending, twisting, folding. The main thing is just like you can memorize what the range of like certain bonds would mean, so you can identify maybe certain structures, certain bonds, or like characteristics of a molecule, like whether it might be a carbonyl, like what kind of peak that would look like, things like that. So that's why I have this little table. This was all I really memorized. So yeah, I think having a few committed to memory is really useful for these for IR spectroscopy problems. And then for NMR spectroscopy, this measures the alignment of nuclear spin with an applied magnetic field. It's calibrated using something called TMS, which has a 0 ppm shift. So you would see it like somewhere over here. Oh, so this is what like your NMR spectroscopy would look like. Here it's also shown what downfield versus upfield means. Just know like what those terms mean, like, oh, if you see an aldehyde, would you expect to see it like more downfield or upfield? And I roughly recommend like memorizing where carboxylic acids show up, aldehydes, aromatics, alkenes, basically like the upper portion of this table. Um, I remember like mildly struggling with this, or like I kept forgetting it. So I highly recommend watching this video. It's called Everything You Need to Know About NMR Spectroscopy. I believe it's by Eightfold MCAT if the video doesn't happen to work for you. But highly recommend checking out that video as well for more info. But yeah, roughly memorizing like a few placements of these will be really useful. Right, and then you have mass spec. This is used to determine molecular weight and help in determining your molecular structure. So your base peak is your tallest peak, as you can see here. Your molecular ion peak represents the molecule itself. So you'll see like the mass of the, or like the atomic mass of the molecule. And so basically what this is like splitting the molecule up into like a bunch of different ways it can be split up, as you can see here. So the molecular ion peak will be the whole molecule. The base peak will be like when they split up this collection of, or like this, like let's say pentane, for example, if they tried to break it up in a bunch of different ways, your base peak is like the manner in which it showed up most. So let's say it showed up as like butane the most often, you would see your base peak at what like the mass of butane is. And then you have your N+1 and your N+2 peaks. These are related to the relative abundance of carbon-13 or these isotopes of bromine and chlorine. And the ratio, I should say ratio, relative to the mass peak. I think you should just roughly be familiar with like these ratios and what these different types of peaks might mean. But yeah, that's a quick overview on mass spec. All right, for separations and purifications, this is what an extraction would look like. So in your organic layer, you'll have organic molecules, or it's like your nonpolar layer. And then in your aqueous layer, you'll have, you know, things like water, salts, stuff like that, like water soluble items. So like if you're asked like where would you expect to see you know, like this salt, you would expect to see it in the aqueous layer. So that's something that you might be asked and related to an extraction. There's also these distillations. Definitely be familiar with these three different types and when each would be used or why a certain type of distillation would be used. It has to do with the relative boiling points of the compounds as well as the difference in boiling points. So you can see I've sort of listed them out for you here. But yeah, distillations will separate liquids based on boiling point. You don't really need to know this setup that well. I didn't, but I have it here if you're curious. And then chromatography. I don't know if any of you guys have done this in lab yet. Maybe you have, but also be familiar with these different types of chromatography. Also know for sure that the stationary phase is typically polar, whereas your mobile phase is typically non-polar. But yeah, different types include gas chromatography, gel filtration chromatography, ion exchange, and affinity chromatography. I think what you might see most often is thin layer chromatography. It's like where you have, at least the one that I did in lab, like we had this paper and we were like things are moving on this solvent front. But yeah, you'll probably see something like this if you do have anything related to chromatography. And then also know for sure how to calculate retention factor. That's that formula is listed out for you here as well. All right. So I think that concludes everything I have on Orgo. I know I sped through Orgo a little bit faster than I did for physics, but I wanted to be mindful of everyone's time. I'm sorry I went over. I'll upload this whole thing, hopefully it recorded fine, as well as a link to this presentation. I'm trying to figure out how I can stop sharing my screen. Sorry. Oh, there we go. All right, yeah, thank you so much for coming. I hope it was helpful. Again, I'm sorry about the whole timing issue, but again, this presentation will be available to you. So thank you everyone for coming. Good luck and have a good night.
Thank you.